Hi, James.
Hey, Andrew, how are you doing?
Yeah, good, thanks.
How's the fall coming along? Is it getting cold, the weather over there now?
Yeah, we definitely feel it's still a little bit warm, but yeah, it gets chilly at night. It gets dark earlier. So yeah.
Right. Hey, Rudy. Hey, John.
Hey, James.
Hello.
Hey, guys.
Good. Maybe I'll give a few more minutes for people to join. Let me start sharing the screen. Interesting. Like let's give a few more minutes. Like I know Tony won't be able to join today. He's travel. I do have a few updates today. We have Andrew, I think has created a list for the material properties for simulation. So he's going to share with everyone in the moment. I think from previous meeting, we decided to have properties that break into a components and also analysis. So I think Andrew will cover the components part from the experience. So and then the analysis side we will pending. I think on the next time I think I can see if we can able to get some action items on it. It's really interesting. Like today has really row head count today. I'm wondering if there anything conflict today, or is there any conference going on? Do you guys know?
That's a good question. I'm not sure, James.
There was a microwave conference, packaging conference going on in Sylvan Cal.
Ah, okay. Is our people attending? Do you know, like from Cadence side or?
Lots of people from Cadence went, but the two people from Cadence who joined this call didn't. So
Oh, okay. I see someone joining from 1000 number, right? Who is that? Can't tell. Yeah, I noticed that Victor, you are new here, or have you joined this meeting before?
James, 100 is me. I don't know why it is showing 100 my my ID number, office ID number.
Oh, okay. Interesting. Yeah, I think maybe sometimes because your phone connected to your computer, it's trying to call in from the voice to your phone, something. I
No,
don't know.
no, no, no. I'm using my office computer.
Ah,
I didn't have Zoom, and just I followed the instruction from the invitation. We are not
Yeah.
allowed to have we don't have Zoom in our office. We are supposed to use only Teams.
Ah,
Probably is that the reason?
I don't know, but well, it doesn't matter. I think since we know you can connect, you can hear, find everything is good.
Okay. Okay.
Yeah. You mind to, I mean, introduce yourself. I think which company you're coming from. I think
Oh, my name is Muthu, and previously I introduced myself, right? My name is Muthu. I represent.
yeah. Oh, Muthu is you. I thought you are Victor. Sorry. Got it. Yeah, I think
Okay.
we know you. That's fine.
I represent Western Digital. I'm leading the Materials Center of Excellence.
Right. That's good to hear that. I thought you were Victor, so I think I was confused earlier.
Okay, sorry.
Well, it's good to have you back. You were on vacation, right? Sometime.
Yeah, I was on leave. Yeah, I went to India. Correct.
Okay. That's good. So, do you know is Pradyumna will be joining?
Yeah. He's supposed to join. We have sent an invitation. He'll be joining now anytime soon.
Okay, sounds good there. Great. Victor, can you hear me, Victor?
Yeah, I can hear. Yeah, I think I'm probably the first time here. I saw the title of the meeting. That's why I'm here. So.
Oh, okay. No worries. I mean, it's welcome. It's open to, it's public, open to everyone. I think that's the spirit of the OCP. Sorry. So, yeah, but maybe Victor, if you can do which company you're from, maybe you can do a quick thing intro.
I'm independent, so actually not even a hardware person, just interested at this point.
I see. Okay. I got it. What's your background? Do you mind sharing that?
Yeah, mostly database actually is my background, and more into security at this point. So just but I've been looking at just getting interested in the hardware as well.
Got it. Okay. Yeah, welcome. Yeah, I think we have a lot of folks have software as well. I think background because we are EDA companies here as well. So we do many of us I think do have both hardware, electrical and also a software background. So but it's nice to have you join here. Hopefully you we will learn something here, and we also hopefully you can contribute as well when you can. So I think we see many people join here. Let's get started. I think already just kind of recap from last meeting. I'm just kind of copy from the next agenda from the previous meeting. So we talk about, I think Jen is not here today. Excuse me. I think Michael just came back, I think from vacation, but I trying to reach him. I haven't heard from him yet. So, but we'll get updates on the GD side later on. But we do have the Andrew. I think will be updating on the the property list that he has prepared for the simulation. So I think on the spreadsheet side. So and a quick update is here is the GitHub. So right now we have I created the GitHub report for the MDK. So it's still empty right now. We just created recently. Let me share with everyone. But eventually we're going to start the moment when we started to have some format the schema. Once we finish that, we can start putting some of the format here. I think for this MTK, mostly we're going to use the, as many discussed before, we mostly going to use with the XML format. So we're going to have XML schema here and also some sample data. And then is the Mike or it's not here. Rudy, do you have any update if we were able to reach out to Keysight for participating?
I don't without going through again my prior company. So I don't.
I see. Okay. Are you still able to, or are you still planning to, right?
I'll try via other methods. Yes.
Okay. Okay. Appreciate that. Yeah, I think that's kind of like reached what we have today. So I probably going to hand over. I think this is the new tab Andrew has created. So we're going to hand over to Andrew.
Yeah, do you I'll just let me share. I'll share my copy because
yeah, sure.
it's just that I can then jump to other documents if I need to. So let me just work out how I share on this.
There should be a button at the below, and yeah, I think once open their main windows, you have to find out which
got
one.
it now. There you go. Should see that now. Yep.
Yep.
Yeah. Okay. Yeah. So I said that I would kind of focus a bit on the material properties for simulation. One of the reasons is, you know, we had a look at this properties tab, and there's some material properties here, but I think if one of the focus wants to be, you know, that we want to provide material properties to focus on simulation, and in particular multi-physics simulation, then there's a kind of a smaller subset of properties which you can use for that. And so one of the things that my team does at ANSYS, you know, because we're part of the material teams that we support all of or most of the ANSYS products with materials data. So we have quite a good view of all the different types of simulation which are performed. And it can get quite confusing. And I think we kind of went into some of that confusion last time, where, well, what properties do you need and what type of simulations are we talking about? And the way that we found is probably the best way to deal with this, you know, because we have 30+ packages that kind of do different types of simulation, is to go back to the basic physics. So rather than talking about how you use the simulation or what type of simulation you're doing, like thermal cycling or signal integrity, it's easier to kind of go back, at least when you're looking at the material properties, to look at the actual physics. So what I've done here is, you know, it's focused on 4 of the main physics, which is electrical, thermal, structural, and optical. And each of these, there are kind of certain subtypes of simulation, like electrical. There's high frequency. There's also low frequency, which is more the kind of magnetic side of things. And I haven't put that in here because I didn't think that was particularly relevant. And then for each of those subtypes, I put the properties which are kind of key. So these are the things that you'd actually measure. So these are the actual material properties. I've highlighted what parameters that these properties mainly depend on. So for these particular electrical ones, there's a frequency and temperature. Often when you kind of get into simulation, there are then models. So simulation tools often will represent material properties as a model that allows you to then capture how these properties change as a function of these parameters. So I've put some examples here of the kind of models that might be representing these particular properties in various simulation codes. And then sometimes there's other factors. For example, surface roughness can be a factor in these electrical properties. Now, this is not meant to be totally exhaustive, these kind of later ones here, but I've just tried to put examples. And I'm not a complete expert in all these physics, so it's just a format that I've put together that maybe, you know, the people who are more experts in particular types of simulation, we can take this format and kind of use the kind of group knowledge to, you know, try to fill this in or fill in some of the gaps or some of the in a bit more detail if we feel we need to.
Andrew, sorry to interrupt you. This is really a great work by looking at it. A doubt that we can say lot of work went in. The quick question is about column E. In your, I mean, this is a very generic format. I understand that. And you said there is a limitation. There are many things to be added. I understand that fully. But the question is, when we are using the models, are we allowed to select? Are we going to provide the users to select the models, or we are just going to give example? For example, in terms of dielectric constants, DKDF, you mentioned generally about the frequency. How the user will know which frequency to select? Are we going to that level, or this is just an education?
No, it's those are critical parameters. And I'm sorry, I didn't catch your name earlier. I don't remember. But having the frequency of interest, this is all things that you would have at your kind of in
your
your
selection.
list
It's a user
of
selection. Okay.
available materials. I mean, these properties, DK, DF, temperature, they're all very standard, at least in the SIPI world. They're givens. You must have those before you can run any sort of simulation. So I think this is very well understood. Anyone involved in SIPI will certainly understand the requirements there.
Okay.
Yeah. So yeah, go ahead.
Sorry, Andrew. Muthu, I think here the objective is not so much about educating the customer as to what frequencies to choose here for the DKA. Sometimes they don't have control. Here, the purpose of this particular forum, right, is to come up with a consistent universal format, standardized format to exchange such information across different parties. So I think that is where the scope is. So what Andrew is listing out is what all variations would be needed. That's what he's saying. He's not picking what temperature to choose. He's not saying what orientation to choose. That's not his him to dictate. Whatever the thing one chooses, how would you go about describing that in a way that vendors don't have interface issues? And that's what this forum is trying to address.
Correct.
Okay. Thank you, Lal, for the clarification. I got it. So it's a very general format. Just those who are in this field or very closer to this field will understand by looking at it. But the selection and all depends on the user, right? Their own particular situation. Yeah. Got it.
Yeah, and one thing to point out is that that these kind of two columns here, these are pretty much universal, because these are things which they're actual material properties, they're things you measure. It's when you kind of get down to here, the models, we have to decide whether you want to go this far, because as soon as you get into the models, you then start to get into probably simulation tool specific models, because I know because my kind of real expertise is around the structural side. That I know that when you get to hyperelastic models, which are used to model elastomers, so you get a lot of kind of these kind of materials on kind of circuit boards, for instance, and there's these models here like Mooney-Rivlin. Now ANSYS has packages that will accept Mooney-Rivlin models, but then you go to other packages from companies like Siemens and Dassault, they will call these the same Mooney-Rivlin, but they'll have slightly different implementations of that model. And so the model I use for my ANSYS software won't necessarily be the same model that I would use for Dassault or Siemens products. And therefore you start to go down that very kind of difficult road of where you get vendor specific data, which is probably going to confuse things. So I've put this here for completion so people understand it, but it may be that we want to limit ourselves to pure material properties, because then you are quite neutral then. For instance, for when you get into structural, if you give the user the stress strain curve, which is the basic kind of structural properties that you would measure, you measure stress, strain, and time. you can then do all this fitting yourself. You know, you can do whatever you want with these for your packages, but this is ultimately what everything is based on. And so this is the more kind of neutral set of data that we might want to represent without starting to get into vendor specific models. That's my kind of point of view, but that's up for discussion.
Yeah, no, I think Andrew, I really like that the way you put it. I think you totally, I think like heavy. I think like from our previous discussion, I think like we want to make it generic. But at the same time, I think like the column E, the materials model is good there. I think like we do have another tab, like the analysis that we talked previously. I think that is kind of like in a way similar to the models, because depends on different analysis you use, you need a different model. So I think it's good to cover some of them, like because like from different models, the parameters might slightly requirement might slightly different, right? So they might potentially have additional properties that might not use in other models. So I think maybe it's good to have that. I think extensive is probably not able to do like inclusive everything. I think like because of limited resources, I think like, but I think extensive as we can, I think like, it's nice to have that. I think, and then that will help to cover the column C and D, the properties and the parameters, so that we can cover, I think, the range. I think like the properties needed, and constraint, I think, with the certain model. So we kind of like have that kind of like format and schema available for people to able to cover that whatever model that they're trying to use. I think I think I from that sense, I think I kind of like agree with that. Does anyone else has any kind of like comment or input or thoughts?
Yeah, I will add, James. I think the material models that Andrew mentioned, right? For now, we are talking about vendor neutral format, right? But there will be circumstances where you will have to, break that, because if the customer, if this is the only way to do it, in some cases, right? Some industries, some companies lead the whole thing. At that point in time, we will they will be creating some of these things with the material models. For example, let's go back to what Muthu was asking, right? The frequency points, right? Sometimes what vendors do is they don't specify dielectric constant versus frequency for all frequencies. They probably mention a causal model called the Joe-Davidsson curve, right?
Mhm.
That requires 2 frequency points. You don't require like 100 frequency points. With that, you can come up with an approximation, right? That might be a way for some people to mention their own model in the first place. And that is a pretty standard thing right now. I will say pretty much every EDA tool supports it. But, there could be other things. So I think we need to have provision to include these things in our format as well. We don't need to think about it today, but I think that might be needed. I'm thinking aloud, thinking in the future.
I think you got a good point there. I do agree on that. I do see that. I think you mentioned, I can see that. I think I've seen before. And definitely, I think, those kind of use cases you mentioned and Muthu pointed out as well. I think, sometimes your parameters might have a certain, I think, relationship or constraint based on a certain model. So for customer using, I think, I think, it's good that I think that's a good point. I think we should note down, and then we should try to cover. I think as much knowledge as we have. I think that's what we're all here.
Lal, let me add something on to it. The reason why I raised that point, we are in the experimental side. Okay, this is nothing to do with this one, but just as you said, we have to think aloud before we put up all this information. Andrew has done really a great job, but the thing which I'm trying to clarify with this audience is, with this group is, what level that we should take it. I know the objective. Now I'm very clear of the objective. We cannot put everything, but if I want to select such a model, all the time the clash between the simulation team versus the reliability team or even the hardware team is about the choice of constants. What model we are using, that's the most critical one. Of course, there are standard models, but for every industry, they have their own problems. For example, in the solder joint issue, now when we all moving towards LTS, low temperature solder, that domain is very new. So there is the model which was created for these 25 years is purely targeted for SAC, predominantly with 305 or 405 in the industry. Correct me if I'm wrong. But now when industry for the last 6-7 years, there is a lot of impetus to push towards LTS, low temperature solder, sustainability, and so on. So now we are all confused with which models. And when you go into the board level, choice of PCB, pre-preg, and go deep into that orientation of pre-pregs at that level, deeper into that level, then the challenge is the frequency. Some of our customers are looking at 20 gigahertz frequency. Does the model help me or not? So where do I go and choose the model? My model may have a limitation in terms of choice of frequency and further on. So these are all the ones I'm thinking, should we address, or it is too premature to talk about that?
Well, I think it's valid to, when we're recording this information, to record over what range it's valid. You know, because over what temperature range can you use this? Over what frequency range can you use it? I think that's valid information to be stored, and so therefore our XML schema needs to have a places to say, well, this is the valid range which people should be using this data over. It doesn't tell, I mean, they can use it outside that range, but at least they know then that, you know, they're outside the recommended range for the data which they are handling.
Right. Okay. Thanks, Milan. Thanks, Andrew.
Yeah, I think the good thing with the XML schema, I think as Andrew pointed out, we can have kind of like set many this kind of optional information, right? I think it has a guideline, so as much as possible, even we can also set temperature range with respect to a specific models, right? We can do that as well, and people can customize on top of that as well. So, but for those why we know industrial standard, we can. Yeah, I think it's always good, right, to provide like suggestion there, right? Including our model, I think like more kind of a reference, but not necessarily have a kind of like restrict that, I think, like, but then as kind of guideline, I think always be helpful.
Yeah, I mean, you know, for each set of data that we're going to represent in the XML, there's going to be a set of metadata which we need to record for each of those. I mean, just things that spring to mind are things like units. You know, that units always trip people up, so we need to make sure we have a clear way to define the units, min and max, recommended range, as we've just discussed, test method. You know, I know when you get to measuring these kind of things here, DKDF, there's different test methods, and you know, and you can often not compare, you know, properties which have been generated from different test methods. So again, that's another area that we need to be able to have a space in the schema to record. So again, when people look at that data or the package, because read the data, they, you know, it's clear what, you know, how this was generated. So I think that's another task for us to define what kind of metadata we want to create spaces for, so the user, you know, has a good idea on whether that data would be suitable for their use case.
So along with that, based on what you told me, right? I think what is clear, crystal clear, based on what you said, is models is going to have the limitation at some point in time. You already pointed out the limitation in your recent the trends in your work, right? So modeling is just you have data, you model with some model. You need to have a way to prescribe the raw data and leave it to the end user to model the way he sees fit, with all the things that Andrew was mentioning, the comments sections, everything put together, right? So I think here, that's what that column D, parameter frequency, right? If you don't have a model good enough to represent what you have measured, then it's you need to have a way to mention the raw data. So this format should mention that. And if you have a model that captures it well, then you can say it, and then say that if there is a model, it's a limitation, then you add the comment. So basically, I think this will provide the different flavors, right? Whatever would be needed for someone to prescribe it, they should provide the provisions for you to say that.
Exactly, Lal. Got it. Yeah, you're right. You're right. We need to have both. Yeah. Thanks.
Sorry, I think Andrew, are you mean to continue? I mean, are you on your presentation, or you are more?
Well, I mean, I don't really want to, well, I could go through each of these, but I don't think it's going to be very interesting. I mean, I think it's, I've basically done the same thing for all the different physics here. I mean, I think we've had a good discussion around about how far we want to go, about what other information we want to capture. I mean, one thing that I don't know how far, because structural can get, I've put a selection of things in here which we might want to capture, but structural can get very complex very quickly, and this is, these are the ones I think we need. I don't come from your industry, so I don't know how far you take structural simulation. I mean, you could say, well, all we do is linear elastic with a bit of thermomechanical. I don't know whether you look into non-linear or kind of failure. So again, somebody with more of your industry knowledge probably needs to go through this and say, well, some of these things we don't need to worry about for the time being, but others, you have, we don't cover this. So so I kind of really tried to get a format which we can all use to kind of contribute, because we all have different expertise, areas of expertise. But if we can stick to this kind of format as I've done it, then I think that will help us to quickly build this up to a kind of definitive list.
Yeah, Andrew, this actually this is very good. Most of these are used in the industry, right, for different aspects of it. But all of this, pretty much anytime you put down you want to build a geometry, you want to build widget, all of these come into play. But one thing that I wanted to ask you is, one thing that we definitely care about is, actually, I'm not sure what the right term for that is, but material adhesion, right?
Yeah,
because we build things from multiple layers of different materials. How is that captured? What is the best way to capture that?
Yeah, there's two. Yeah, that's a good point. That's something I haven't considered. Normally you can treat a bond, if we're talking about adhesive bonding, in two ways. You can either treat it as a material itself, and then it has things like, it has a modulus, it has a strength, and you just model it as another layer, or you treat it as a interface and you don't model the material, and then you're looking at I can't remember the word they used to describe it now, but it's not something I've got here. It's the kind of bond strength you would then look at. And there's a set of properties which I haven't got here, which I can probably add into here. Yeah, the term that I need to I use is, I can't remember what the term is, but there's a because when you look at an adhesive layer, it can either fail through the adhesive, or it can fail at the bond line, and we haven't captured here that kind of bond line simulation. So yes, but I can look that up and add it to here.
I think at the bare minimum, definitely the interface aspect, interface bonding aspect, would definitely be of interest. But one thing that comes to question, I know that we're talking about it, is that will be basically the bonding between two different materials, right? It's not a property for one of the materials, it's property of the two materials.
It is, yes. It's an interface property, yeah.
Would that be then part of the, where would that live? I mean,
well, but you would still, you'd still represent, because it's being bonded together by something. And so, and that material is behaving as an adhesive. and it may not have like bulk properties, but it would have these adhesive properties. So it could still be a material, but it would have more kind of bonding properties rather than kind of bulk properties.
David, let me add for a few things here. We have some experience on it.
Mm-hmm.
When you talk about adhesive nature, there are two things to note down. One is about the material itself, what type of adhesive. Okay, that's the first choice. The second choice about where do you apply this adhesive between two? Is it the same class of materials or two different class of materials? That's the second thing. But to do that, to find the adhesive nature, the surface properties of where do you apply this material is also very, very key, because the surface free energy determines the adhesive nature. If I'm going to put it on a metal, then the surface energy of the metal material is critical here. So is it a OSP, is it a PCB, is it a FR4, or a metal itself, or a polymer? All these things come into play. So there are many more things, layers are there, not just adhesive property alone. That's very simple, but looking into where we apply is also another factor. So do we want to go to that details? Then it has to be expanded.
Yeah, what I was thinking is, say, if you take, for example, a PCB, there is really no adhesive material that gets added, right? You just add one layer, add the second layer, bake it, add another layer, bake it, add another layer, bake it, right? So in the end of this process, out of these multiple layers, things will be bonded together in some way. Mm-hmm. So I'm thinking, where would that live, right? Where would that property live? Because it's kind of in the material, but then it also depends on the whole bonding process as well.
Yeah, I think like maybe to summarize, I think David may be looking for, is there any like model or some way for this kind of composite material, right? It's not a single property anymore. How to model that?
Yeah. I mean, composites can get complicated. But if you're bonding pre-preg together to make a PCB board, then wouldn't you treat that as just a single material, or do you then start treating it as individual layers bonded together?
Right.
Yeah, again, it depends on the type of simulation, right? If you really want to find out if this board will delaminate at some point, obviously you have to go and do individual layers, maybe on a small scale, but still find out how good that bonding is given the application, whatever simulation is necessary. Maybe it will be bending the board at high temperature a little bit more than what you would expect, right? Maybe high G forces at high temperature, right? Would those materials still hold together?
Yeah.
Right.
I mean, generally, that if you've got a composite, then you would then apply, you'd look at failure, that you're looking for failure of one of those layers, and one of the failure mechanisms might be delamination. But that is a complex field, and I'm surprised that you'd get to that level. People normally treat laminates, just to make it more simple, as a orthotropic material, so it has different properties in different directions. But unless they're particularly interested in, I come from the aerospace industry, so we would look at where a kind of bolt or a cable goes through, and that's a stress concentration, and then you model that kind of hole in a lot of detail, or the individual layers, to understand whether the stresses would start to delaminate. But you wouldn't do that across the whole wing, say, because that's far too complex.
Of course.
So I think it's just, I think if you can say, well, we do that in certain cases, then we need to worry about it. But I think that's where, like I say, that the industry experience needs to kind of guide this and saying, well, how much detail do we need to go to?
Yeah, I think I would say that we do that in kind of in a similar fashion. Obviously, we cannot simulate the whole PCB or anything like that, but small areas we want to focus down and see what's actually going on there. And for that, definitely would be interested to do simulation with the bonding strength and see if anything will peel off or things like that, right? And especially this is probably true a lot more for the whole assembly process, right? Where the temperatures are very high typically than what you would have in normal operation, right? And then all the materials behave differently. They're going to bond differently, and then the stresses are going to be totally different too. So again, I'm sorry, I distracted everybody with my question here. Just I was curious whether it's worth putting the bond strength as a property, and how would we do it if it's simple to do, or if it's way too complicated to do, and we should think about
Well, I mean, it's certainly two areas, that composites are one thing and then bonding is another. That's two areas that we could expand this into. I could certainly, look at the composites. That is actually my background, so I can add a few extra bits of information here about how you'd represent that. I'm not. Somebody was mentioning that they have quite a bit of experience in kind of bonding. Maybe they could, tackle bonding. I'm not sure. It's a bit hard to say who was speaking, but I'm not sure who kind of mentioned that they were.
That is Muthu. He's actually from Western Digital.
Yeah.
Okay.
Yeah, Muthu, do you have that experience, or can you share that information?
Yeah. Actually, that we can add from our side once Andrew completes it. Actually, we got a quite good experience. We use a different type of material software that is very specialized on building layers one by one. We do it for PCB, prepregs, and so on, epoxy resins, and so on. So that helps us to do mean field homogenization technique. It's called MF modeling, and we go by layer by layer. And then we can do all kind of strengths, mechanical, thermal, loading can be applied, and we can see the whole strength of Young's modulus and other Poisson ratio and things like that. All thermomechanical information can be simulated. So these are all pretty much available. We can share what we can do from our side. Definitely, we can add some spice to it. David, we can assist on that. No problem.
That would be awesome.
Right. So Muthu, are you mentioning you're able to share some information, or you're able to help to put some information in this spreadsheet?
I will add some information once Andrew completes this document. I can add some more things.
Got it. Sounds good. Yeah, appreciate that.
Andrew, on the composites, you mentioned composites. I think it's going to be great if we can define materials which are composites of other materials, kind of reference those. That would be perfect. Because in many cases we just get information for the base materials, and somebody has to by hand go and calculate the stuff. So if there's a way to automate that process, that's going to be super, super helpful. And one question about that though, in composites, there's a variation in the final material, right? Meaning in density. Is that something that can be captured? Is that data available? Is it capturable?
Do you mean variable in density because of the manufacturing process, or because of the different?
Yeah. Basically, the manufacturing process. Well, there may be multiple reasons. One is the manufacturing process. The second one is, right, if you are mixing, let's say you're mixing a, I don't know how to say this, I'm not an expert, but say you're mixing a hard material which comes with different granule sizes with soft material, you will get differences, right? Is this capturable somehow?
Well, yeah, I mean, the two ways that you can represent composites really is, that you either, and this isn't really about the properties. This is about the materials you're capturing. So you either capture the properties of the, say, the cured laminate. So you know what stacking sequence you have, you know what thickness you have, for instance, and you capture the properties of that cured laminate. But then that's only then valid for that particular stack up, you know, that you've represented. But then you treat it as a homogeneous material, and don't worry about the fact it's got fibers or particulates in it. You just treat it as a homogeneous material, but with different properties in different directions. The other way is then you start to then capture the properties of the constituent parts. And I think that's what Muthu was talking about, where, you know, you'd capture the properties of the fibers, you capture the properties of the matrix, i.e. the polymer matrix. And then you use some other tool to take those component properties, and you use this tool to kind of build it into a composite. And then that tool calculates the kind of final properties of that composite, and that's what you use in your simulation.
Okay.
And that's a lot more flexible, because you then take your two components, and then you can build any laminate you want, and you've got the properties. But it's often hard to get the properties of those individual components, like the fibers or the particulates or the, you know, the resin itself. Often you don't get those published. That's the kind of best way to do it. It's the most complex way, but it's the best way because it's very flexible. But it can, it's harder to do. Plus, it's harder to get that data. But then the properties you're capturing are exactly the same as the ones we have here. It's just the way that you are defining them on a much more granular basis, which you then have to kind of build up into the material that you actually use.
Okay.
But that shouldn't affect the properties themselves.
Would that composite final, the material property for the final material, for the composite material, in the end of the day, have a variation in it, or would it be global range, kind of min-max values?
Yeah, I mean, again, that's another level of detail. I mean, a lot of people will just use the average properties or the minimum properties, which they expect to get. But you can then start to do, you know, bring in statistical variations, you know, saying, well, at some point I might have a 40% glass fiber, and other places I might have a 45% glass fiber. That will give me a 10% range in my properties.
Yes.
So it just gets very complex very quickly, and I just worry that we can get really, really complex really quickly.
Yeah.
And maybe we are going into too much detail for the edge cases, and maybe we should focus on the kind of, you know, the 90% or the, you know, the 80% of what people need.
Yeah.
Get that defined. Yeah.
Yeah, I agree with that. Just this was a curiosity question. Wanted to find out how these properties vary. But yeah, I agree with you. We need to focus on the most important parts.
Yeah.
Okay. Thank you very much for the good discussion. I appreciate it.
Yeah, that's great information. One thing I want to throw back in here is about that the components. I think like since we have this materials models, right? So the models typically they kind of like difference also. I think for different component. I think when we talk about that composite earlier, different layers, right? I think it depends on where you use that, right? Where you use that in substrate. Like substrate also have multiple layers too, right? And then or on the IC or on the PCBs, right? So I think they're all kind of different. So maybe I think when we do that model, maybe I think it's good to kind of like also like include that component and see that where's that model mostly used, and then that's kind of help to also kind of like cover, I think like the more accurate, I think like that model, right? Like all this kind of DK, DF, right? I think reticle they use in many places, right? You can use in the board, right? For connecting right, all the pins of the chip, right? Or it can be on the RDL, right? Receiver area. That's another connectivity. You could be using this kind of DK, DF as well, right? So yeah, I'm just kind of throwing out there. Maybe we can, when we do that, put that model information, like we also kind of like can maybe break that down according to components. I think that would be helpful to let people know. I think where's that model mostly used in which components or which area or what is covered.
Okay, thank you, thanks.
So when you say components, do you mean these kind of components?
Yeah, whether PCB or silicon substrate or like whether using like some like bumps and things like that, right? They're all some of these things like they have also at some level has like reticle like properties like to be analyzed and cover there and also like dielectric, right, and others like thermal and mechanical.
Okay. I mean, so I can do a little bit more work to this, but I would encourage people to, this is all shared, isn't it? So this is in the Google Docs thing. So I think I said that, that I just add a bit more information about composites into here, about some of the properties you might need if you're looking at composites, particularly PCB laminates. But yeah, I think everyone needs to take a look at this, and then we can, open it up to a bit for people to include in here. I mean, just there's a couple of other things I just noted here. Long-term effects. I think this came up last time. People were saying, well, what about the long-term effects? That when you have, how the properties change after it's been exposed, to high temperatures or to radiation or whatever other environments. So, we'll have to have a think about that because generally you don't have models for that. You might have a value of the, some of these properties, in their kind of virgin form. So after it comes out of the factory, and then you might measure it after, that 2 years exposure to radiation and find there's a degradation in certain properties. And then you just record those. But there's no kind of systematic way that you can do that. So that's just one thing to think about. And then the other thing to think about is that this is just the properties you use for simulation. So there are lots of other properties. I mean, things like, one of the things I notice here, we've got things like glass transition temperature, so TG. So so if you're doing a material selection, that's an important property to know because you want to choose a material that has a glass transition temperature, which is outside the kind of temperature range of which you're operating at. But you wouldn't necessarily use that glass transition temperature in simulation. So there might be a set of other properties we want to include, which will allow people to understand that material they're looking at, but may not necessarily be used in simulation.
Right. I think yeah, that's a good point to capture there. And as far as
again,
that,
yeah, go ahead.
No, I just want to look back the previous one you mentioned about the degradation of this kind of properties. There might be some formula, right? Something that people use, and there's some commonly used one, right? I mean, maybe we can kind of include those. Do you know any of them? I think there may be some. I think I kind of maybe not formula, but there's some kind of statistic information, right? For some plastic material or something like that. I think or they might kind of or conductivity might kind of get certain percent. I think degradation, something like that. That's kind of thing that what you mentioned here, right? I think is there some information that you think you've seen somewhere that can point out have some sort of formula or maybe tables that can be referenced to, so people, I think, can be captured here.
Again, I think that I'd be looking for people who have experience in this industry to say what they usually see. I mean, again, just from my experience, which is not relevant, but from aerospace experience, moisture is a big contributor to degradation of composite structures. So you'll often see what they call hot-wet properties of composites, which is when they've been exposed to high levels of moisture for a long period of time. So you'd often use those hot-wet properties in your design because they include all the degradation you might see over time. Now, when you're in the semiconductor industry, like you guys, you might say there's other long-term effects which are very common, and you might find data, very commonly to show the effects of those of that degradation, and we should try to incorporate that somehow. But again, I think that's where you guys with the industry expertise can help guide. But what's the usual data that you see about how properties or how materials are degraded over time?
Yeah, that makes sense. I think there's one thing I think I've seen that before, it's like a reform profile where you put that back in oven, every time you put different layers on top of that. I think that's an impact. I think on the materials that's already on top, and that going through that reform profile many times. So we do see, I think there's some characteristics change on those materials. That actually one of things that caused some bugs that we used to have debug for a long time. So, but we're familiar on that. Yeah, but just want to find out if there's any formula and things like that that out there. But it seems like this is is probably very kind of specific field. I think I really need to a specific expertise on this. You point out.
Mm-hmm. Yes, I think I brought this to a level where that from my kind of general knowledge, I can add to it. But then I think the next stage is for some industry expertise to start to kind of guide this to what's really important. What's really important for your industry to capture, because we could spend many weeks capturing everything we can think of, but I'm sure there's a much shorter list of things which are the most important to tackle to start with.
Right, that makes sense. Yeah. I think we almost time. I think so Andrew, you cover most of it, right? So here I think okay, that's good. I think I really appreciate that. I think that's a good starting point. So I think you're going to add a few more composite we talked, right? So I think after that we're going to add more on top of that as well. I think with the bondings and things like that. I might look into a bit, see how I can maybe add a bit structure on that model, to cover some of the components to help people, guide people the models according to different area components to that. And then hopefully I think others can chip in there. I think from the industry expert, and I think expanding on the model sides and also some of these long-term effects, whatever the knowledge they have. That's good. That's good. Is this the last line you talking about the multi-physics simulation? Are you meant to talk something about that, or something that you already covered?
It's just that that when we come to this page here, I mean, we talk about different types of simulation, like power integrity, thermal cycling. My kind of point here was that normally those types of simulation are just a combination of these physics. And so once we've captured this, we should have all the properties we need to cover, these more complex types of simulation, because ultimately they are normally just simulating physics, but different, but simulating combinations of physics. So that's why I started here, and then maybe again we can then start to build up and say, well, what combination of properties do we need for these, or what combination of physics do we need in these for these? But but I think we should probably focus here first, and then once we get this clear in our heads, then we can start to build it up to other types of simulation
Yeah,
all these.
or even internally, ANSYS has tools that do that too, right? So you could check with those internal teams. Right.
Yes, exactly. Yeah. Yes, that's right.
Yeah. Like Sherlock or the Res products. Yeah.
Yes, exactly. Yeah. Yes.
Sorry. Yeah.
That makes sense. I think, I think we start from here. I think when we also cover the analysis, then we can start also connecting the dot between the two, and then see what things that can be including more here. I think yeah.
Okay.
Yeah, that's good. Appreciate Andrew. Like, anyone has anything else, or if not, I think we are on top of the time right now, so we will continue to cover next one. Like after we have more updates on this spreadsheet. If not, then appreciate everyone for the time and the contributions, and we'll talk to you again next time. Wish you Friday and
Thanks, everybody.
Yeah, great weekend.
Cheers. Bye.
Thanks, everyone.
Hey,
Thank
Bye.
you. Thanks.
Bye bye.